Well, I think the state of the art is quite a varied thing. It's a moving feast. Ask 5 different people, they'll give you probably 8 different examples of what the state of the art is. But there are certain avenues that are beginning to sort of get a lot of attention. If you sort of think about the work that's been done at DeepMind, which is probably a good example, how they started off looking at getting machine learning models to play what apparently seems to be like rather trivial tasks like playing video games, particularly Atari games. That's an interesting problem because it combines some of the kind of deep neural network supervised learning models with another technology called reinforcement learning, which is the idea, and a lot of things in life are like this, when we address problems where we don't get feedback straight away as to whether we're right or wrong. You make a classic example is you make a move in a game of chess and you don't find out till 4 hours later. But that was a critical one that cost you the game, for example. So their work was combining this sort of the latest trend in using very big neural network models with many layers. There's 2 reasons we can do that now. One is we have very powerful computers and we have a lot of parallelization. A lot of work is done on GPUs, graphical processing units, and indeed Google have their own tensor processing units or TPUs. So this means we can number crunch all this data. And data, again, is the key thing. These models have huge numbers of parameters. It's all been exposed to statistics in the past or the concepts required for parameter estimation. You need huge amounts of data that correspond with huge amounts of parameters in your models. So we're able to use much more complex models because we now have the huge amounts of data that we need to be able to fit those models in a sort of statistically robust way.